All right, as promised, I have a couple torque problems for you guys. You can see both of them at the top of the page right now, but we're going to start with the one on the left. We have a construction worker holding a uniform 3.0 meter long 2x4 that has a mass of 7.7 kilograms. One of the construction worker's hands pushes down at one end of the 2x4, and the other hand pulls up a distance 1 meter from that same end of the 2x4. How much force must be exerted by each hand of the construction worker to hold the 2x4 level? So the 2x4 will be at rest, so we can treat this as a statics problem. But first, it might be a good idea to draw ourselves some kind of picture here. So we have a construction worker holding the 2x4, which I will draw in gray here. So there's the 2x4, not exactly a 2-scale drawing, but we'll work with it. And we want to make a free body diagram of all of the forces that are acting on this 2x4. So, first of all, the 2x4 has mass, so anything that has mass will have weight acting on it. And then in the problem statement, it said that one of the construction worker's hand, the one at the very end, pushes downward. So I'm going to call this FD for force down. And the other hand pulls up. I'm going to call this FU for force up. So it might be helpful to have a few distances labeled in this problem. It did say the distance between the construction worker's hands was 1 meter, and the entire length of the 2x4 from one end to the other was 3 meters. From here, we can begin to start writing our equations. If you have a statics problem, there are two things you'll know about that statics problem automatically, and that is that the forces are balanced and the torques are balanced. So let's start off with the forces. The sum of our forces equals 0. We really only have the y direction here, so I'm just going to define up as positive. Always need a coordinate system where vectors are involved. And writing our F equals ma equation, as we normally do, the upward force minus the weight minus the downward force all have to combine to give us 0. So this by itself doesn't tell us a whole lot. And we have two unknowns, so we can't solve for either of them with just that equation. Then, after that, we could write our sum of the torques equals 0 equation. We'll need a coordinate system for this as well. I'm going to have counterclockwise be positive. And to write a sum of torques equation, you need to choose a pivot point. And there are many different ways we can choose a pivot point, but let's choose our center of mass as our first pivot point. The center of mass being where the weight is acting from. So this black dot right here will be our first pivot point. So because the weight acts directly at that pivot point, we will not need to include torque from the weight because the weight will not exert any torque about that pivot point. The lever arm would be 0. So the only torques we need are the torque from the downward force and the torque from the upward force. And those will add up to equal 0. Now we just have to consider whether these torques are positive or negative. So if we imagine kind of sticking a pin through our pivot point, the center of mass, the downward force, FD, would try to make this thing rotate counterclockwise. So that torque is positive. The upward force would try to make this 2x4 rotate clockwise, which is negative in our direction, our coordinate system. So using our equation of torque equals Fr sine of theta, I'm just going to note now that our theta will equal 90 degrees for everything. So you'll see me leaving off the sine of theta term because sine of 90 equals 1, but I have at least included in my solution that I did consider the theta term. I'm not including it for a reason, and I've made that reason clear. So the torque caused by the downward force will be whatever the downward force is, times our lever arm for that downward force, times sine of theta, which would equal 1 here, minus the upward force times the length of the lever arm for our upward force, which equals 0. Now we need to find the length of our lever arms. So for the downward force, RD, the lever arm for FD in this case, is the distance from the force to the pivot point. Since this beam is uniform, that means the weight force acts right from the middle of the beam, 1.5 meters from the end. So that means, our lever arm for the downward force is 1.5 meters. Our upward force we also do not know, but our upward force lever arm is the distance from the upward force to the center of the beam. So this would be RU, and then this whole distance here would be RD. If there's 1.5 meters between the center of this board and the edge, and 1 meter of that is taken up between the construction worker's hands, that leaves 0.5 meters left for the lever arm for the upward force. Now, since we know the mass of the beam and we could calculate the weight, we have two equations with two unknowns. So we could stop right now and just solve a system of equations with those two equations, or there's another way we can do this here. So let me set up another net torque equals 0 equation for you, with counterclockwise as positive again. But this time, let's put our pivot point at the point where the downward force acts. If the net torque is 0, we can set our pivot point wherever we want to. So now, in this blue setup, this is our pivot point at one very end of the beam. So the upward force exerts a positive torque, and the weight of the beam exerts a negative torque. But since FD acts directly at the pivot point, it does not exert any torque. The lever arm for the downward force is 0 with this particular pivot point or fulcrum. So that's it. This equals 0. Again, sine of theta is going to be 1 because theta is 90 degrees for everything. So we just need the upward force times the lever arm for the upward force minus the force of weight times the lever arm for the weight. And that all has to add up to 0. The upward force, lever arm, is going to be the distance from the pivot point to wherever the upward force acts. So this RU here, this is going to be a different lever arm because we've changed our pivot point. So you'll notice RU has different values in this black colored solution and the blue colored solution, and that is okay. Because we've moved our pivot point, it should be that way. But we get 1 meter for the lever arm of the upward force, and we get 1.5 meters for the lever arm of the weight. And the weight equals mg, or 7.7 kilograms, times 9.8 meters per second squared. And we can plug that in for weight, and then our only unknown is Fu, and we can solve for the upward force and get a value of 113.2 newtons. So by choosing a clever pivot point, we've managed to avoid having to solve a system of equations. However, there is a downside to this, in that we only got one of our unknowns. From here, we could take this upward force and plug it back into our first equation up here at the top, our F equals ma equation, or we could plug it into our other torque equation that we already wrote for the center of mass as the pivot point down here, or we can just write ourselves a brand new net torque equals 0 with a coordinate system, and this time let's make the location of the upward force the pivot or fulcrum, which means now this green dot is going to be the point around which we sum all of the torques. The downward force is exerting a counterclockwise torque, which is positive, so TD is positive. And again, the torque caused by the weight will be negative, and those have to add up to 0 because the upward force is acting directly at our new pivot point. The lever arm would be 0. So from here, plugging in from our torque equation, the downward force times the lever arm for the downward force minus the weight times the lever arm for the weight, both have to add up to 0. And plugging in, FD we do not know. RD now is this distance that I've labeled in green. The distance from the pivot point to whatever force we're talking about. And that is the same as the distance between the construction worker's hand, or 1 meter, minus the weight, which was our 7.7 kilograms, times 9.8 meters per second squared, times RW, the distance from the pivot point to whatever force we're talking about, labeled in the diagram up above. Sorry, that's getting a little cluttered up there. And this lever arm, a lot like RU in the first problem, will be 0.5 meters. And those add up to give you 0. And if you do a little bit of math, you find that the downward force exerted by the construction worker is 37.7 newtons. So that's this entire problem. You wouldn't need to do everything that I've done. You could get by with showing just the blue section and just the green section. That would be enough to solve the problem. Or both of the black sections with some extra math to solve the system of equations. Or you could do the blue section first and then do your sum of forces equations. As soon as you have enough equations to match the number of unknowns you have, you can just beat it with the math hammer from there. But these are all of the possible equations that you can write for this setup. Well, not all of them, but the sum of torques equations, the 3 of them that we did right are all possibilities, and the sum of forces equation that we have up at the top over there. Now for another problem, we want to make a balanced mobile for your child. If you don't know, a mobile is like a balanced hanging contraption made of strings and hanging objects that hang above babies' cribs a lot of the time. And the mobile we're going to try to construct has a 0.7 meter long rod. So here is our rod. And we're going to hang a toy with a mass of 2.1 kilograms from the left end. I'm going to call that mass 1. And we'll just write over here, mass 1 is the 2.1 kilograms. And from the opposite end of the mobile, we're going to hang a slightly smaller mass, M2, where M2 is 1.2 kilograms. The mobile rod itself does have a mass, and I'm going to call this MR for the mass of the rod is 0.2 kilograms. And then the question we want to answer is, how far from the left end of the mobile should we tie the string so that it remains level? So hopefully your intuition is telling you that we're going to need to tie it closer to the heavier mass in order for these to balance. So I'm going to draw my string over on that side, make that more straight up and down. And the problem itself asks for how far from the left end of the mobile. So this is going to be the distance we're looking for, and I'm just going to call that x for now. And the mobile itself has a length of 0.7 meters. That's just from one end of the rod to the other. Let me kind of shade the rod here in a little bit darker. There we go. So with all of that set up, this is going to be a statics problem, and we know that because everything needs to stay level and at rest in order for this mobile to be properly balanced. So we can treat this as a statics problem, and that tells us what kind of equations we can write and what we need to do from here. So first thing to do is draw ourselves a free body diagram, which I'm going to do in red. We will have one weight force acting down from one end of the mobile, weight force 1 from the first mass. A weight force acting down from the other end of the mobile, weight force 2. The rod itself will also have weight because it has mass. I'm going to call this WR for weight of the rod. And then there will be a tension force acting upward on the string that holds the mobile to the ceiling. So here is our free body diagram. And we can start writing ourselves a sum of torques equals 0 equation or a sum of forces equals 0 equation. So I'm just going to start with the net force equation, just because it'll probably be easier to write. I'm going to take up to be positive, and we'll see what we can learn from this one equation. So upward forces, just T, and downward forces, we have weight 1, weight R of the rod, and the weight of mass 2, and those all have to add up to equal 0. So hopefully you can see right now that just from the sum of the forces equals 0 equation, we can calculate the tension in the string. The tension in the string is going to be equal to the sum of the weight forces that are all pulling downward. So that's mass 1, 2.1 kilograms, the rod, 0.2 kilograms, and the other mass, 1.2 kilograms. So the total mass times g, 9.8 meters per second squared. So the tension in that rod turns out to be 34.3 newtons. So just from the F equals ma equation, we were able to determine what the tension in that rod, or tension in that string, will have to be. But this isn't going to help us figure out where we need to tie the string, because F equals ma only cares what direction the forces point, not where they act. For us to figure out where the forces act, we are going to need to write ourselves a net torque equation. And then to write a sum of the torques equals 0 equation, we need a couple things. We need a coordinate system. I'm going to have counterclockwise be positive again. And we need to choose ourselves a pivot point. So we're hoping x comes into our solution somewhere, but especially if you didn't do the net force equals 0 problem first, then the tension would be an unknown. So if you don't know the tension force yet, right where the tension force acts might be a great place to put your pivot point. So let's have the string be our pivot point here. So because the pivot point is right where the tension acts, tension will not cause any torque with that particular pivot point. So we just need to consider the torques caused by the other forces. Weight 1 is trying to make this rod rotate counterclockwise, so the torque caused by weight 1, torque 1, will be positive. The other two weight forces are trying to make this mobile rotate the other way, clockwise. So the torque caused by the rod and the torque caused by mass 2 will both be negative, and those have to add up to 0. Again, theta is going to be 90 degrees for all of these, so I'm going to leave off my sine of theta terms because sine of theta will equal 1 for all of them. So based on torque equals Fr sine of theta, where theta is always 90 degrees, the torque caused by weight 1 is whatever force is causing that torque times the lever arm associated with that torque. And the same thing for the rest of these. The torque of the rod is caused by the weight of the rod. Not all forces make a torque, but all torques come from a force. Times the lever arm of the rod minus weight force 2 times the lever arm associated with weight force 2 equals 0. Now we need to figure out what our lever arms are, especially including x in our definition of the lever arm if we can. So for weight force 1, m1 times g is weight 1, and the lever arm is the distance from wherever weight 1 acts to the pivot point. So this is our R1 in this problem, which is the same thing as x. The weight of the rod is the mass of the rod times g, and R of the rod is the distance between the force in question, the weight of the rod, and the pivot point where the tension acts. So we need to find some way to express R subscript R in terms of variables and numbers we already know. The easiest way to do this is to recognize that the weight of the rod acts downward from the center of the rod. So from this point of weight to the left, we've got a total of 0.35 meters. But we don't want that whole 0.35 meters. We want the part that's not already taken up by that x. So what we can end up writing is 0.35 meters, which is half of the rod, minus the distance x, which gives us the distance we're looking for. Then for the last one, we have m2 times g times, again, the distance from the center of rotation of the pivot point to the force in question. This is R2. So you can see that that's the whole length of the rod minus the distance x. So that's 0.7 meters minus x. And that all equals 0. From here, we do have to do a little bit of math foo. So this mg for the rod has to be distributed in to both terms inside the parentheses, and the same thing with m2g. Put some little arrows on those. Making sure that you don't forget that there is a negative sign out in front of both of those weights. So either you're going to need to bring the negative sign in when you distribute with the mg, or you need to leave the negative sign outside and put parentheses around the whole thing. So just to write the next line for you, just so people can see what it should look like, we have m1gx minus mrg times 0.35 meters plus mrgx. So this is what I mean. The negative x and the negative in front of mrg cancel each other out. Minus m2g times 0.7 meters plus m2gx equals 0. This would be a good time to start plugging in actual numbers and then kind of standard algebra at this point. Some of our terms have x's in them, group those together. Some of our terms are just numbers, group those together, and eventually work through this to be able to solve for x equals 0.26 meters would be our final answer. So we will want to tie this string 26 centimeters from whichever end of the rod has the larger of the two masses. These are relatively straightforward torques problems, or statics problems, but these are the types of questions that I would ask on the final exam. Ones with not too many forces acting, with nothing too complicated going on, but you will be expected to work through problems like this on the final exam. That's all I have for you today, and I will see you all in class on Monday.